participation in the fourth Mathematics National Seminar. Now I will going to give you a short presentation about the resolution of the nonlinear programming, entitled by an iterative projective interior point method via majorant function for nonlinear programming. I begin with an introduction in which I will talk about the linear and nonlinear programming and the Kerr-Markov method for solving the linear programming. Then I will extend the Kerr-Markov algorithm in the nonlinear case. Firstly, I define the problem formulation, the transformed problem, the linearization, the optimal solution, and the step size. Then we study the convergence, the algorithm, the general algorithm of Kerr-Markov, and we prove the efficiency of our study by numerical tests. And for sure we finish by a conclusion. Introduction. The linear or nonlinear programming is the process to minimize a linear or nonlinear function subject to linear or affine constraints. In 1948, Kerr-Markov proposed a new polynomial algorithm to solve just the linear programming. And since of its polynomial type and theoretical properties, we think to extend the resolution of linear programming to the nonlinear case. The problem studied is minimize a nonlinear, convex, and differentiable function f, in which the optimal object value z start is known from the beginning. Now, we know the value of z start, we just need to solve the x start. Subject to constraint the ax equal b and x positive. The matrix A is full rank matrix. And for sure there exists strictly interior point x, 0.
The matrix
such that
the matrix A is not square. Matrix A is not square A.
No.
You have system linear. You have system linear.
Système linéaire, oui, c'est ça.
Ok, continue.
D'accord. La matrice A, c'est une matrice rectangulaire.
Ok, c'est clair.
D'accord. The principal idea in the Kerr-Markov algorithm is to transform the X original space to Y transformed space. Kerr-Markov had a problem in a space in a polyhedral or simplex. He made a transformation to another space. From the first space, minimize f of x, he transformed with transformation tk to another space. First, Kerr-Markov worked in a polyhedral. Now, he transformed the problem in a simplex. The first thing in the algorithm is to obtain a strictly interior point. Then, at any iteration k, we transform the point xk to the center of simplex A. At each iteration, the point xk will be the point A in another problem. Now, from the point A, we must calculate an optimal step size alpha and descent direction tk to get a new point, which is yk. Firstly, we begin by xk. Then, after the transformation, we get the point A, which is the center of simplex. From A, we get another point, which is the point yk. From A to yk, we just need a descent direction and step size. Now, when we get the yk, it must reform from the simplex to the polyhedral. From yk, we have the inverse transformation tk to get the next iteration xk plus 1.
How about inverse transformation? Also exists?
Yeah.
Any condition?
Transformation of Kerr-Markov, c'est une transformation dimensionnelle. Cette transformation, jusqu'à maintenant, est unique parce que la transformation du Kerr-Markov réserve les propriétés de le premier problème. The first and the second problem are equivalent. Now, generally, to calculate the next iteration, xk plus 1 from xk, we work in the same problem and the same space. But now, we need another space, the simplex. We can calculate the next iteration directly. The important concept in this algorithm are the projective transformation, the linearization. As I say, the function which I will minimize is a nonlinear function. But the algorithm of Karl-Marx works just with the linear function. Then we need the potential function to calculate the step size and to study the convergence. The Karl-Marx projective transformation is defined by here we have the y equal tk of x. But the problem is that x is in Rn, but y is in Rn plus 1. For this, Karl-Marx calculate the yi from 1 to n low, and he gave that the yn plus 1, the last component, equal to 1 minus the sum of all the components. The inverse transformation of Karl-Marx is directly equal to. Now, as I said, let's transform the first problem to the second problem. Instead of minimize the function f of x, we minimize the function h of y. The function h of 1, first we have f of x. Now we have f of tk minus 1 of y. That start is the optimal value from the beginning. Here we transform the constraint, the first and the second constraint, and as we say that y is a point from the simplex. Now, as I said, we must linearize the function h. Generally, to linearize the function, we just need the development of Taylor. But in our case, we have in trouble if we choose just the development of Taylor. The development of Taylor is a majorant of a function. It's a linear approximation, but it is majorant, not majorant. But in our, when we must calculate the step size, we use the majorant function technique. So for that, for avoid the problem, we don't work with the tangent, we add the parameter beta. But when we add the parameter beta, we must to ensure that the tangent be sequent of h. Now, when we calculate beta, we define the new problem. The h of y become linear approximation, a linear majorant approximation of h. Here we calculate the optimal solution of the problem 6. We minimize the linear function subject to this constraint. We just firstly replace the y minus a by x. Then we have two Lagrange multipliers lambda and mu, and with simple calculate, we get that x start equal and the descent direction dk is defined by. And finally, as we said that x equal y minus a, so the y is a plus x. And x start is minus alpha r dk. And we replace by the inverse transformation of Karl-Marx to get the next iteration xk plus 1. Here, in the yk, the formula of yk is defined by the alpha and dk. So dk is calculated but the alpha is must to calculate. And for calculate the step size, we define the line search function theta, which defined by the potential function P associated to the first problem, which defined by. And with simple calculation, we have the formula of theta. Here the proof how to calculate the theta. Now, for calculate the optimal step size, we can't solve the equation. The first derivative of theta equals 0. This equation is impossible to solve directly. For that, we choose to calculate the step size by another function, which is the majorant function of the search line function. This function is a majorant function of theta and have the same properties as theta. Here the optimal step size is given explicitly by the first derivative of the majorant function. For the convergence, we just prove that the h in the point yk is less than the h of a. These two, the lemma and the theorem, general algorithm of our approach. We begin by initialization, in which we have a tolerance of epsilon and x0. In the iteration, we need the stop test, which is the fxk minus z. Here we have two fixed example. The first is, and the second. The first method is the majorant function technique, and in the second we calculate the step size by the classical line search wolf. Here we remark that the number of iterations in the first method is less than the second method, and with a fewer time. The second example is an example with variable size, and we remark the same in number iteration and the time.
What do you mean by method 1 and method 2?
The first method is the majorant function technique, and the second, the classical wolf.
Okay.
In this work, the goal is to solve a nonlinear problem using the potential reduction of kernel based on a majorant function technique. Firstly, we extend the resolution of linear programming to nonlinear programming. The technique of linearization based on the development of Taylor and the translation, and we calculate the step size by the majorant function technique. Here are some references that we use in this work, and thank you for your attention.